All right, today we're going to define free energy in terms of enthalpy and entropy. We're going to explain the relationship between the sign of the free energy change and whether a process is spontaneous in the forward direction. We're also going to discuss the relationship between delta G to K and E. So at this point, we've been working on Quest 19D and Quest 20 on the first and second law. Hopefully this clarifies some of the questions there. So we've talked about this equation a little bit already. Delta G naught equals delta H naught minus T delta S naught. Something to remember, delta G is always in kilojoules per mole, and then we've got delta H in kilojoules per mole, and temperature is in Kelvin, and then you have to remember that delta S is in joules per mole Kelvin. So when we are trying to figure out our answers to these problems, oftentimes you're going to have to convert your kilojoules to joules and vice versa. So we've talked about a lot, especially in the electrochem unit, when delta G is equal to 0, the system is going to be at equilibrium. And this is going to be very important. This relationship is going to come back. We used it a lot in electrochem. We said delta G is equal to negative rat link. The other form you'll see is that delta G is equal to delta G naught, which is at standard conditions, plus RT natural log of K, or of Q. Another reminder is that K is equal to Q at equilibrium, so EQ. So one of the examples we have is they're asking about what is the boiling point of the solution, where the delta H vaporization is 23.5 kilojoules per mole and delta S is 34.5 kilojoules per mole. Okay, well they gave us delta H and they give us delta S. We can use this equation up here to solve. We know that when we're looking at the delta H vaporization process, all of the particles are in an equilibrium with each other as they're being converted from liquid to gas, right? Everything's at the same temperature, therefore they're at equilibrium. The only thing that's changing is that the energy is being applied to breaking them apart from their more ordered state to the more disordered state, and vice versa. So we can actually say that delta G equals 0 in this situation. So we want to know what the boiling point is. We can say that 0 is equal to negative 23.5, not negative, sorry, 23.5 kilojoules minus T, and then my delta S, which is 34.5 joules per mole Kelvin. All right. Well, it doesn't really matter. Oh, sorry, I had a slight typo there. It doesn't really matter how many moles here. We could just assume 1 mole. But when we go to solve, we have to make sure that our units match up. So we can either be in both kilojoules or both joules. I like going to both joules. It's just easier to look at. So let's rewrite this here. We could say that this is 23,500 joules per mole for delta H. Okay. So to solve, I want to move my terms over. I get a negative 23,500 joules per mole. And that's equal to negative T times 34.5 joules per mole Kelvin. All right. I divide by both sides by negative 34.5 divided by negative 34.5. My units would end up canceling here. The negatives cancel and we get a positive temperature change, which makes sense because we want our boiling point to be a positive number, right? It takes a lot of energy to boil something. So if we plug that into our calculator there, let's turn this thing on. Negative 23500 divided by negative, was it 34.5? Yes, 34.5. All right. And we get a temperature of 681.15. That is in Kelvin. And we have 3 sig figs here, so we get that the temperature is equal to 681 Kelvin. And that does match up with my answer. So it's pretty easy to solve. We just have to remember this is the key here, that delta G equals 0 at equilibrium, and then we can solve. Also remember that if you have elements in the standard state, delta H is equal to 0 kilojoules per mole. That will also help us kind of shortcut our way through some of these problems that we're doing today. This is really important. The relationship between temperature and entropy definitely affects spontaneity. We know that things that have a positive entropy are more spontaneous, but overall delta G is the determiner of spontaneity. You can have really exothermic reactions. So this one's really exo, and they create disorder. Doesn't matter what temperature it is. If you have a negative number and you subtract a really positive number, it's still going to be more negative, right? So delta G in this case is going to be super negative. When we have endothermic reactions, but they still create disorder, this is dependent on a high temperature. If you could have a really large positive number here, if we have a high temperature times our positive entropy, then it will be more negative. So you can have something that absorbs a lot of energy, but if the amount of disorder it's creating at those higher temperatures is greater, then it's going to overpower that amount of energy it needs to absorb, and then delta G will become negative in that case. So negative at high T. All right. Now, there are exothermic reactions where it creates order, and those ones are tricky. At high temperatures, if it's creating too much order, then it's going to end up with a positive. So it's positive at high temps, but negative at low, right? And then you have endothermic reactions that create order, and those are usually non-spontaneous at any temperature. So you need some sort of assistance to make those reactions happen, because there's no way they're going to happen on their own. All right, so free energy in equilibrium. As I said earlier, we have delta G equals to delta G naught plus RT natural log of Q, or sometimes we'll see it where Q is equal to K because it is at equilibrium. And it says one method for synthesizing methanol involves reacting carbon monoxide and hydrogen gas. Calculate delta G at 25 degrees for this reaction. And they give you pressures this time. So something we need to be aware of with pressures, we're talking about our Q. Remember, Q is your reaction quotient where you have products over reactants, and you need to pay attention to the coefficients. Okay. Now, they gave us pressures here. You can also have a Q where it's the pressures are involved, and when we have pressures involved, we refer to K as Kp. Now, with pressures, we only account for those things that are in the gas state. So when we make our Q, actually, let's go ahead and make our Q now. On the product side, we don't have any gases, so we can just put 1. We have 1 over the pressure of our CO, carbon monoxide, and then the pressure times the pressure of H2. But remember, we have to count for the exponents. That has a coefficient of 2, so we do have to square it. Okay, so when we put in our numbers, we've got 1 over 5 ATM for my carbon monoxide times 3 ATM for hydrogen, and that's squared. All right. 3 squared is 9, and 9 times 5 is 45, so my Q is going to be equal to 1 for 45 in this problem. Okay, we are going to plug that in for natural log of Q later on. All right. First, we need to figure out delta G. So delta G, we have to look at the products minus the reactants. So we can figure that out fairly easily using our table here. So delta G, same thing, is equal to the sum of my delta G products minus delta G, sum of delta G reactants. I keep forgetting that sum button thing. Okay. Delta G reactants. Okay. So the nice thing is, because we have hydrogen here, the delta G of hydrogen is going to be 0 in this case. And I can confirm that with the table. If we look at our table, we've got methanol is up here. So methanol in the liquid state, and delta G is in the middle column here. So we've got negative 166.23. So negative 166.23, and that is for 1 mole. This is for my 1 mole of methanol in the liquid state. This is kilojoules. And then we're going to subtract my value for CO, and technically H2, but if we go back and look at H2, H2 has a delta G of 0 right there. So we'll ignore the 0 for now, but we can go to CO. CO has a delta G of negative 137.2. Alright, so negative 137.2 kilojoules per mole. And what the heck, I'll put in here, 2 times 0 kilojoules per mole for my hydrogen. So this is for the hydrogen gas, this is for the CO. Okay. Alright, so when we calculate that out, we get negative 166.23 minus, what was my number? Minus a negative 137.2. Alright, we get negative 29.03 kilojoules. So negative 29.03 kilojoules per mole, and this is delta G naught at the standard state. Alright, so given that it's delta G naught at the standard state, we can figure out what delta G is using this part of my equation, delta G naught plus RT natural log of Q. Alright, so we got negative 29.03 kilojoules per mole. Now, the R that we're going to use, remember that R has units, it's the 8.314 version, and this is units of joules per mole Kelvin. So I'm actually going to go ahead, save myself some trouble, and make this delta G naught in joules. Alright, joules per mole. Alright, plus 8.314 joules per mole K times, they say it's at 25 degrees Celsius, so we need to put that at 298 K. And then my natural log of 1 over 45, which we calculated up here, right? That's my Q value. Okay. So let's see what happens. So I'm going to do the natural log first. Natural log of 1 over 45 times 298 times 8.314. All right. That is in joules, so negative 9431 plus negative 29030. All right. And I get negative 38,461 joules. I'm going to convert that to kilojoules. So negative 38.46. And let's check my numbers. Looks like we only have 2 sig figs in this problem. All right, so I'm going to get negative 38 kilojoules as my delta G for this reaction. Okay, not bad. Let's evaluate. Is this a spontaneous or non-spontaneous reaction? All right, should have said spontaneous because of the negative delta G. Okay, we've got a couple more examples here. This time we're going to solve for our equilibrium constant. So we have the Haber process here. It's the ammonia synthesis reaction. It is called the Haber process. So if you hear anyone say Haber process, that's this reaction here. We are just creating ammonia by combining nitrogen and hydrogen gas. All right. So we know that delta G is going to be equal to negative 33.3 kilojoules because that is our delta G reaction. So delta G, and then this is going to be plus my RT natural log of K, and they tell us that it's at this is times K. They tell us it's at 25 degrees, so we know it's 298 K. Now there's one key piece of information here. What are we trying to calculate? We're trying to calculate the equilibrium constant. If we're calculating an equilibrium constant, what does delta G equal? Should have said delta G equals 0. So we really have this bit of information here. And I'm actually going to take the moment to convert this to joules. We know that this many joules for our delta G naught plus 8.314 times 298 times natural log of K. This is what our system is. If we move our terms around, we get natural log of K is equal to 8.31 or 33,300 joules. 8.314 times 298. Let's simplify. All right. Oops, I forgot a 3. And then 8.314 times 298. We get 13.44. So 13.44. Natural log of K is equal to 13.44. So what do we need to do to solve for K? That's right, we've got to raise everything to the E. So e to the natural log of K, this cancels. We would get K is equal to, let me move that over here. We get K is equal to e to the 13.44. We've got e to the 13.44, which is 680, with 3 sig figs, 687,000, which is huge. 687,000 is my K. All right, let's think about what a large K means. Is this going to be a favorable process or an unfavorable process? You should have said that it is favorable. Products are going to be favored because it's a large K. You can also tell that it's spontaneous because of the negative delta G that we normally have. This is a very favorable reaction, even though it is creating some order. Okay. All right, and I think this is my last one. Like we said earlier, sometimes you might have to calculate the pressures. This is a a good problem. And this one's tricky because it's a good exercise of the Q and what the different states mean and what we include in our Q quotient. So we have to look up our delta H and our delta G's, I believe, and our delta S's. Well, actually, sorry, we don't even need to look at delta H. We can just do our delta G's on this one, sorry. So delta G, let me find my delta G values for CO2. CO2 has a delta G of negative 394.4 kilojoules. So this is negative 394.4 kilojoules per mole. Alright, let's find my lead. So PB lead is right here. Okay. So PBO is negative 187.9. Negative 187.9. And lead carbonate is negative 625.5. Okay. Negative 625.5 kilojoules. Alright. So if we do delta G, we know it's products minus reactants, and we have to account for the moles. Luckily, it's a 1-to-1 ratio for everything. So we get negative 394.4 plus negative 187.9, and we're subtracting negative 625.5. All right. Clear everything out, got a nice clean slate. Negative 394.4 plus negative 187.9, oops, 0.9, minus negative 625.5. And we get 43.2 kilojoules, okay? 43.2 kilojoules, and I'm going to do myself a favor and just make that into joules. 4320 joules per mole. And then I've got the same equation as before. I know that delta G equals delta G naught, and I've got RT, natural log of Q. All right. At equilibrium, what does delta G equal to? Delta G is equal to 0. So 0 equals 43200 plus my R times 298K, natural log of Q. Okay? Alright, so I get negative 43200 divided by 8.314 times 298. And this is going to be equal to natural log of Q. We get the negative because I just moved my terms over and we divided to get natural log of Q by itself. So this is equal to negative 43200 298 times 8.314. Alright, so negative 17.43. Negative 17.43. Alright. So we can solve for Q, e to the negative 17.43. So second e raised to my answer. I get 2.68 times 10 to the negative 8th. 2.68 times 10 to the negative 8th. Now, because I'm looking at pressures, this is equal to Kp. Alright? And I know Kp is going to be equal to the pressures of my products over the pressures of my reactants. Well, the nice thing is when we're talking pressures, the only thing we're looking at is CO2. You might have been inclined to say PCO2 times the pressure of PBO over the pressure of lead carbonate. However, you got to remember that lead carbonate and PBO are solids, and so they have no business in your Q. So Q is actually just equal to P of CO2 over 1, which would just be P of CO2. So since we have this is equal to Q, which is equal to Kp, we also know that this is equal to our pressure of CO2. That is a really, really low pressure. Oh, and let's think about it. Is this a spontaneous or a non-spontaneous reaction? If we look at our delta G, this is a non-spontaneous reaction. It makes a lot of sense that we didn't make much gas because it's not very favorable, right? We have a very small Q because we have only a little bit of gas being formed. Okay, I believe that is all for today. Yeah, we're not doing that problem. Okay, have a great day.